What's up, Organickers? Today we'll be taking y'all through electrophilic aromatic substitution, otherwise known as EAS.
So the history of the reaction is that it was discovered around the 1870s to 1880s, which was a very long time ago. It's a broad reaction with several specific types under its category, and so there really isn't one scientist who came up with the reaction. However, two scientists who came up with Friedel's Kraft alkylation and acylation are Charles Friedel and James Kraft, hence the name of the reaction. Alkylation and acylation are two important types of EAS that allows you to add a carbon chain or carbonyl to a benzene ring.
Alright, so now y'all are probably wondering, why is this reaction important? EAS is the primary way that chemists can functionalize a benzene ring. Most of y'all's reactions probably haven't specifically involved benzene until now, but there are many ways that it can react. For an everyday life or medical example, pharmaceuticals like ibuprofen are made using EAS steps. Along with that, many polymers, plastics, and dyes are also synthesized through EAS.
For the general mechanism of the reaction, benzene acts as a nucleophile because it's stable, an electron rich with all of the pi electrons that it makes, and it wants to attack a positive charge, so the nucleophile will attack a positively charged electrophile, and this breaks the pi bond in the benzene. And this is a slow step because you're breaking the aromaticity and it makes a carbocation intermediate. And then in the next step, since it has the carbocation intermediate, the benzene ring becomes the electrophile, and a nucleophile attacks the hydrogen, and the hydrogen puts the pi electrons back into the benzene ring, re-aromatizing the ring. And this is the fast step because it's breaking the hydrogen rather than breaking an aromatic ring.
Now for the different types of reactions. So there's 5 main types of reactions in EAS. The first is halogenation or bromination. The second is aromatic nitration. The third is aromatic sulfonation, and remember that reaction is reversible. The next two are Friedel's Kraft alkylation and Friedel's Kraft acylation. And the difference between those two is that alkylation can have rearrangement, and so sometimes you have to be pretty specific when you're using that reaction. So the first reaction that we're going to go over is bromination. This is the first one of the 5. And in the very first step, we have to make the electrophile so that we can get benzene to react later on in the mechanism. So the very first step is that the bond between the two bromines here come and directly attack the Fe molecule right here. And what happens is we get bromine and FeBr4. So in the mechanism here, we start with benzene and it comes and attacks bromine, which then will give us a bromine group here with a hydrogen, and it'll create a carbocation right there. In the next step, we'll start with this that we just made in the first step. And we now have FeBr4 that is now going to act as the nucleophile, and it's going to come and pull off this hydrogen right here. And this hydrogen will come down and re-aromatize the molecule, and that will send us straight to product with a bromine group attached and HBr. And the reason why in these reactions that the nucleophile isn't attacking the carbocation like they typically have in previous reactions is because if it does that, it will not re-aromatize, and therefore it has to pull off the hydrogen so that can happen.
The second form of EAS is nitration, and so you start with nitric acid, and in this reaction, the nitric acid is going to pull off one of the H's and H2SO4, and this leads to this intermediate where the hydrogen is going to break off and it leaves you with nitronium and water. And so you're able to use this nitronium ion in the EAS reaction. And so in this, the pi bond is going to attack the nitronium ion, and it's going to form the intermediate right here where it has the nitro group off of it and a hydrogen. And so then after this, the HSO4 group has a negative charge, so it's going to attack the hydrogen right here, and the hydrogen is going to put the electrons back into the benzene ring and re-aromatize it, and so you're left with a benzene ring with an NO2 group off of it. And then with this reaction, you can also turn it into an aniline using hydrogen on palladium on carbon, and it can create an NH2 group instead of the NO2 group.
Next up is sulfonation. And in sulfonation, remember that this reaction is reversible, so in all the steps I have arrows going both directions. And this reaction allows you to add sulfur trioxide to benzene, and the reagents that we use are SO3 and H2SO4. So first up, to make the electrophile, we have sulfur trioxide, and a lone pair on the oxygen up here will come in and grab this hydrogen right there. And that'll create the oxygen-hydrogen bond that I have up here, and HSO4 minus as well. And to start off this reaction, benzene, once again, as the two previous reactions, we have this group, the pi bond will come in and attack the sulfur, and that'll send us to our intermediate over here with a carbocation right there. And the next part of the reaction is a base will come in and attack this hydrogen, pull it off so that it can re-aromatize. And once again, we get our final product right here. The fourth reaction we have is Friedel-Crafts alkylation. And in this reaction, there's a few limitations that we have to be aware of. So the first one is only alkyl halides can be used. The second is this reaction is not feasible on rings containing an amino group substituent, and is also not feasible on rings containing a strong electron withdrawing group. So if either of those groups are on there, then there'll be no reaction. And lastly, we really have to watch out for rearrangement. And in this reaction, the first step is we have the bond between CH3 and Cl will come in and attack the aluminum right here. And that will give us our methyl group and AlCl4 minus. And the next step down here, we'll use the methyl group, and the benzene pi electrons will come in and attack the methyl group, which therefore will attach right here, and it gives us our carbocation intermediate. And from there, we'll use AlCl4 will come in, just like the other reactions, pull off the hydrogen. The hydrogen bond will drop down to re-aromatize it, and we are left with our major two products.
The final form of EAS is Friedel-Crafts acylation, and this is really similar to alkylation. There's just a lot less limitations to this reaction since it is more stable with the oxygen group off of it. And so the first step is the bond in the chlorine is going to attack the aluminum, and this leaves a carbocation and AlCl4. And so very similar to all of the other reactions, the pi bond in the benzene is going to attack the carbocation right here, leaving to this intermediate, which is going to have this group off of it with a hydrogen. And so the chlorine in the AlCl4 is going to attack the hydrogen, and the hydrogen is going to put the electrons back into the benzene ring, re-aromatizing the ring and leaving this as your major product with HCl. And then with this reaction, you can also add hydrogen and palladium on carbon onto it, and this can reduce the reaction into a simple ethyl group. And that's everything on EAS reactions. These are the citations of the sources that we used to make this presentation, and thank you so much for watching.